Welcome back to Electronics Explained Simply. Before we jump into today's topic, we're going to start with something new, a short quiz. This quiz is based entirely on Episode 1, where we covered electric current, voltage, and power. The goal isn't to trick you or test you under pressure. It's simply a fun way to check your understanding and help lock in the fundamentals before we move forward. So grab a pen, think through each question, and see how many you can get right. Don't worry, we'll go through the answers together. Alright, let's start with the quiz from Episode 1. Question 1. What is electric current? The answer is... Question 2. What is the unit of electric current? The answer is... Question 3. What does 1 ampere mean? The answer is... Question 4. What actually moves inside a metal wire? The answer is... Question 5. Why do electrons move when a voltage is applied? The answer is... Question 6. What best describes voltage? The answer is... Question 7. Why does current start flowing almost instantly when you flip a switch? The answer is... Question 8. In conventional current flow, current flows from... The answer is... Question 9. What is the correct formula for electrical power? The answer is... Question 10. A device uses 12 volts and draws 2 amps. How much power does it consume? The answer is... Welcome back to Electronics Explained Simply. In this episode, we're going one step deeper and introducing resistance, Ohm's law, and how different materials affect the flow of electric current. These ideas explain why current flows easily in some cases, and why it struggles or stops entirely in others. To understand resistance, we need to zoom inside a conductor like a copper wire. Inside the wire, electrons are not moving smoothly like cars on an empty highway. Instead, they constantly collide with atoms in the crystal lattice, impurities, and even other electrons. These collisions limit how easily electrons can move forward. This microscopic opposition to motion is what we experience macroscopically as electrical resistance. Early scientists couldn't see electrons or atomic lattices, so instead of focusing on microscopic behavior, they studied what they could measure: voltage and current. Georg Simon Ohm discovered that for many materials, increasing the voltage caused a proportional increase in current. From this observation, resistance was defined as the ratio between voltage and current. This relationship is written as R equals V divided by I. In words, resistance is how much voltage is required to produce a certain amount of current. If a circuit needs a lot of voltage to push even a small current, it has high resistance. If a small voltage produces a large current, the resistance is low. So what does 1 ohm mean? 1 ohm is defined very precisely. A material has a resistance of 1 ohm if 1 ampere of current flows when 1 volt is applied across it. This definition gives us a concrete reference point and allows resistance to be measured and compared between materials and components. Ohm's law is empirical. Despite its name, Ohm's law is not a fundamental law of physics. It is an empirical rule, meaning it describes observed behavior rather than explaining why it happens. It works very well for many materials, but not all. Some materials and devices behave very differently. Ohmic versus non-ohmic materials. Materials that obey Ohm's law are called ohmic materials. In these materials, resistance stays constant over a range of voltages and currents. Non-ohmic materials do not behave this way. For example, a diode allows current to flow easily in one direction, but strongly resists current in the opposite direction. In these cases, resistance is not constant, and Ohm's law does not apply directly with. Resistance depends on geometry. Resistance is not determined only by the type of material. It also depends on the physical shape of the conductor. Two important geometric factors are length and cross-sectional area. Effect of length. As electrons travel through a wire, each collision slows their forward progress. The longer the wire, the more collisions occur. Because of this, doubling the length of a wire doubles its resistance, assuming the material and thickness stay the same. Effect of cross-sectional area. The thickness of a wire also plays a major role. A thicker wire has more available paths for electrons to travel. This reduces congestion and lowers the number of collisions per electron. As a result, increasing the cross-sectional area of a wire reduces its resistance. Current density. This idea leads us to current density. Current density describes how much current flows through a given area. A thin wire carrying a certain current has much higher current density than a thick wire carrying the same current. High current density leads to more heating and greater energy loss. Introducing resistivity. So far, we've talked about resistance, which depends on both material and geometry. To isolate the material itself, we introduce resistivity. Resistivity is a property of the material alone and does not depend on length or thickness. It tells us how strongly a material inherently resists the flow of electric current. Resistivity equation. Resistivity is related to resistance by the equation Rho equals R times A divided by L. Here, A is the cross-sectional area, and L is the length of the conductor. This equation allows us to compare materials fairly, regardless of shape. Conductivity. Some engineers prefer to think in terms of conductivity instead of resistivity. Conductivity is simply the inverse of resistivity. A highly conductive material allows current to flow easily. A poorly conductive material resists current strongly. Both concepts describe the same physical reality. Comparing materials. Metals like silver, copper, and aluminum have very low resistivity and high conductivity. Semiconductors such as silicon have much higher resistivity, but their behavior can be controlled. Insulators like glass and rubber have extremely high resistivity and allow almost no current to flow. Temperature effects. Temperature also affects resistance. In most metals, resistance increases as temperature rises. This happens because higher temperatures cause atoms to vibrate more, increasing collisions with electrons. This effect is described by the temperature coefficient of resistivity. Water as a conductor. Pure distilled water is actually a good insulator. However, most real-world water contains dissolved ions. Salt water conducts electricity well because the ions carry charge. In liquids, current flow is mainly due to ion movement rather than electrons, air, and breakdown. Air is normally an insulator, but if the electric field becomes strong enough, air molecules can be ionized. This allows current to flow through the air, resulting in sparks, corona discharge, or lightning. Electrical breakdown occurs when the insulating property of air fails. Vacuum. A vacuum contains no free charge carriers and is normally a perfect insulator. However, electrons can be injected into a vacuum using heat, light, or strong electric fields. This principle is used in vacuum tubes and other specialized electronic devices. Summary. Resistance arises from microscopic collisions inside materials. Ohm's law describes the relationship between voltage, current, and resistance for ohmic materials. Geometry, material properties, and temperature all influence resistance. Understanding these concepts is essential for analyzing and designing electronic circuits. That wraps up this episode on resistance, Ohm's law, and material properties. In the next episode, we'll start with a short quiz to test your understanding of what we've covered so far. So make sure you're ready. After that, we'll continue by diving deeper into some very important topics. We'll look at insulators, conductors, and semiconductors, and what really separates them at a physical level. We'll also talk about heat and power in electrical systems, including why components get hot and how that affects circuit design. Then we'll introduce thermal heat conduction and thermal resistance, which are critical concepts in both electronics and PCB design. And finally, we'll cover wire gauges, current capacity, and why wire thickness matters more than most people think. If you're enjoying this series and want to build a solid foundation in electronics, make sure to subscribe.